Hello everyone, welcome to the linear elasticity class. In this video, I'm going to discuss the principle of minimum total potential energy. This is one of the variational methods or a principle that would be used for solving boundary value problems of linear elasticity. So I'm just going to give a little bit introduction to compare this method with the previous method that we already discussed, which depend on the Newton's laws which is commonly known as the Newton's method of linear elasticity. So as I mentioned in the early lectures, in the start of this class, we derived the equations of motion and the boundary conditions based on the Newton's method. In this method, basically, we derive the dynamic equilibrium of the system of particles. We started from the system of particles, which would then generalize for linear, for elastic continuum. Like we started from the discrete system, we assume a discrete system of particles, then we derive the equilibrium equations or the equations of motion of a single particle. Then we consider the summation to sum all the dynamic equilibrium of the system of particles. Then we did integration and we applied the divergence theorem, if you remember, to end up with or to drive the governing equation or the equation of motion of the elastic continua in general. That would be composed of an infinite number of particles. So this approach or this method basically, and forming the equations of motion, was dependent on the Newtonian method or the Newton's law of the dynamic equilibrium, that the sum of forces is equal to the inertia force in the other side. Then we use the governing equations for solving boundary value problem. Then we discuss the governing equation. This governing equation includes the displacement field as degrees of freedom of the particle, the kinematical variables, which are the strains, the kinetical variables, which are the stresses, and how we can form them, the constitutive equations. Then we discussed the equilibrium equations or the equation of motion. Then we discussed the boundary condition. But the key idea here about, so the approach of Newtonian, the approach depends on assuming a displacement field, as I mentioned, driving the kinematical variable, the stress field, then the substitution into the equilibrium equations to end up with some equation, differential equation or partial differential equation, that should be mathematically solved. And in order to solve these equations, and this is what we typically did for when we solved one-dimensional problems, like as I mentioned here, that we started by assuming a displacement field, then we formed the strain field, the stress field, then we plug these stresses into the equilibrium or equation of motion or equilibrium equations, as long as we are working in static, and we end up with some ODEs or partial differential equation that we should be. Partial differential equation definitely in case that we are working two dimension, but in one dimension it's going to be ODEs. So then we solve these ODEs, and when we drive the general solution, there was some constants, and in order to find these constants we had to use or apply some boundary conditions, right? So along these quantities and equation, boundary conditions should be defined. But if you remember that when we discussed the boundary conditions, even for the problems or example that we considered using this Newtonian method, that the formation of the boundary condition depends mainly on our understanding of the structure or the continuum or the material that we're already considering. Like the formation of the boundary condition definitely will be different from one problem to the other, and there is no specific way for forming these boundary conditions unless you understand how these boundary conditions are working for this specific problem or this specific structure. But if you struggle in understanding these boundary conditions, you're gonna find it difficult to find these constants or to end up with a final solution or to solve the model that should be solved using this Newtonian method. So this is one of the challenges of using the Newtonian method, especially forming the boundary conditions. To understand the boundary condition, other methods are preferred, like the variational method, and this is the thing that we are going to discuss through this video. Make sense? So in this method, we used to define some boundary conditions based mainly it is based on our understanding of the structure or the continuum that is under consideration. Whereas using the aforementioned approach, which depends directly on using the equilibrium equation that we had derived based on the Newton's method. So that's why this approach is commonly known in the field of linear elasticity, like we are using Newtonian's method to solve for linear elastic or boundary value problem of linear elasticity. Whereas this approach or this method or Newtonian method for solving elasticity problem is applicable, you could say that to all structures and material. We can use it for any structure. Some structures, such as beams and plates, their kinematical variables, which are the strains or the kinematical variable, like stresses, are formed differently than they appear in the governing equation. In the governing equation, in the Newtonian method, or even the equilibrium equation or the equation of motion, depend on the stress field, right? Like we write the equation of motion into this form, like sigma ji comma j plus fi equals rho ui double dot, right? So here we have to deal with the stress as a stress. This is in the Newtonian method, right? But in beam structures or plate structures even, we are using other measures like the bending moment, like the normal force. So these are other forms of the stress. We are not dealing with the stress as it is as a stress, but instead we are dealing with it like a bending moment or another measure. So to do so, if we decided to work with the Newtonian method, we have to change this form. This classical form of the equation should be changed into to represent the moment here, because one of the essential features of beams that they support bending moments. So we have to form the bending moment in terms of these stresses. We would find it difficult for us to do so using the Newtonian method, but if we understand that we are dealing with a beam, we can do, like, for example, some multiplication with z variable with some parameters here, and we do changes but these changes that we can do over this conventional form of the equation of motion mainly depend on our understanding of the structure. But if we don't understand how this structure is working, so we're gonna find it difficult. And even if we decided to apply the Newtonian method or this formal form of the equations of motion equilibrium equation, we're going to find it difficult to understand the main features of this structure like beam or plate, for example. And there are some other more complicated even structure that it would be difficult if we decided to use this Newtonian method for solving their boundary value problems. Make sense? So this is one of the challenges of that we usually face when we consider the Newtonian method. Also, in addition to this, in more complicated structures, or even when implementing advanced theories, like in the project, you are required to use a couple stress theory, or use the non-local theory, or even there is the micromorphic theory. So these advanced theories, their boundary conditions are not conventional. And the Newtonian method, our understanding, or we form the boundary conditions in the Newtonian method mainly based on our understanding of the feature or the structure or the linear elasticity problem in hand. But as I mentioned, in more complicated structure and more complicated or advanced theories, we're gonna find it difficult to form this boundary condition. And the best way to do so, we have to use a variational principle or a variational method to do so, so we can have a clear vision, an insightful understanding of the boundary condition of this structure. It would be difficult to understand the natural boundary condition, especially their relation to the essential boundary condition. We said that the natural boundary condition, this is the type of boundary condition that depend on, that is defined in terms of the stress field or the force field, right? Or definitely the force, it is a form of a stress, another form of the stress. The essential boundary condition, this is the type of boundary condition that depend on the displacement, that we're gonna give displacement or prescribe displacement to a certain surface or boundary of the continuum. So these are the challenges that we're gonna face when we consider the classical method or the Newtonian method for solving boundary value problems of linear elasticity. The other approach, which much more practical and it is used and it is very useful in solid mechanics in general, is the variational principles. That you're going to use one of the principle of the variational methods or variational principles to solve or to drive the equations and all the parameters in addition to the boundary conditions for linear elasticity boundary value problem. Okay, so what does it mean, the variational principle, and how it works? First of all, something that you should understand, that all the equations, all the governing equations, the boundary condition that we use to define or consider or drive it based on the Newton's laws of dynamic equilibrium, we can drive them back again the same using the variational principle, one of the variational principle or method. Variational principles have played an important role in solid mechanics, as we mentioned, and it's gonna be clear as we discuss next. One of these variational principles that we are going to discuss through this video is the principle of minimum total potential energy. If you remember, even in the dynamic class or even the vibration course, that you used to solve the problem using one of the two methods. One of the methods is the Newtonian's method that depends on the sum of force equal the inertia. This is the Newton's law. And the other method is energy method. The energy method, all the energy methods are variational principle or variational methods that we can use for the linear elasticity or solving boundary value problems of linear elasticity, as it's going to be clear. So one of them is the principle of minimum total potential energy that we are going to discuss here. So this principle actually is a variational principle or a variational method that can be regarded as substitute to the Newtonian's equations of equilibrium of elastic bodies. This is the good thing of this, or it would substitute the Newtonian's method. So you could say that solving these linear elasticities, we do have two main approaches: the Newtonian method that we already practiced and we did over different examples for one-dimensional problems before. Also, the other approach is using these variational principles. The use of the variational principles makes it possible to have an insightful understanding of all the parameters of elasticity problems. This includes definitely the governing equations. We said that in some special structures like beams and plates, it is recommended we have to reformulate or rewrite again the equilibrium equation in a form that shows the bending moment instead of showing just the stress. The stress and bending moment, both are stresses, by the way, but they are different forms of the stress. So we need the form that shows the bending moment. This is much more suitable or convenient or consistent with the beam and plate structures. The Newtonian's method, we have to do changes to this one that mainly depend on our understanding. But basically, using the variational method, we're gonna find that it will be automatically obtained, and we're gonna understand the main reason behind this new form, why we have to define or depend on a bending moment in the beam or plate structure, and for other structure, that is fine to just the stress. And the boundary conditions also, we can understand them well using the variational method. As I mentioned, in case that would have more advanced theories or more complicated structures, we won't gonna able to understand this their boundary conditions unless we achieve or use one of the variational methods. In addition, the variational principle is the backbone of nearly all approximate methods or approximate solutions, like the finite element method, Ritz method. There are lots of other approximate methods that would be used. All of them depend mainly on variational methods for solving boundary value problems of elasticity. So, as I mentioned, we're gonna use this variational method here to formulate the governing equations and everything as we did before. We're gonna do it using the variational method. Then I'm gonna show you how we can apply these things to beam structures. So starting, since we're gonna talk about the total potential energy or the principle of minimum total potential energy, so we have to understand what does it mean potential energy and how we can form this total potential energy first, so we can do minimization to this potential energy. So one can understand, you could say that this is my understanding of the potential energy, that we can understand this potential energy as the amount of energy needed to allow the object to move or to deform or to do anything without any external assistance. The key idea here that there shouldn't be any external assistance to this object. This is the key point here. Like, for example, and one of the examples that you used to consider in the dynamic class, if we do have here, or even the static course, assume that this is a table in this way, and over this table we're just putting an object on the top here, like there is an object on the top of this table. So with respect to this ground, which we're going to consider this one as our datum, with respect to this ground, this object has potential to move down. But because of the table, we are preventing, or we are not giving the permission to this object to move. But anyway, it has potential to move. There is a stored energy inside this object that this object gonna use it when it is needed to move it down. And this is gonna happen unless we just remove the table. If you remove the table, this object is gonna fall down. Why? It's going to do something, it's going to move, so this object requires energy to do so. This energy is already embedded, stored inside this energy, but it is not shown because of the table. But once we remove the table, this object gonna use it, gonna record this energy, and it's gonna use it, and the object gonna use it to move it down, or to move down, to be dropped over the surface. So we're going to say that this object that has some stored energy. This stored energy is a potential energy that gives him the potential to move without any external assistance. The other option is that we can try push the object with a very high force in such a way that it would break even the table, so this object is going to move down. But here the movement that came to the object, it mainly came because of external assistance, of external energy. This external energy is the work done. So the work done is different than the potential energy. The potential energy is something that the object is stored inside the object, and the object gonna use it to move. Another typical example is the spring, right? The spring, for example, if you do have a spring in this way, and you let us assume that the spring is fixed, and this is the spring, okay? And assume that you are going to compress the spring. So pushing the spring in this way, you are exerting some force. You are exerting some work over the object to push it, right? So this spring will be compressed. But what's gonna happen once we remove the force? The spring will restore back again. Why? Because this is how it works, that the spring absorbs this work that you give it to the spring to compress the spring to a certain displacement. So you are already exerting some force, exerting some work, some energy. You are giving some energy. The spring gonna absorb this energy and store it. And once you remove your hand, the spring gonna use this energy to recede back again. So this stored energy inside the spring, this is a form of elastic energy. This is a spring energy. This is a stored energy. This is the potential energy. This energy what give the spring potential to recede back. Without this energy, the spring won't gonna able to recede back again. So how the spring recedes back to the original dimension, or the original length, the undeformed length, it restores back because of this potential energy without any assistance. This is the key point, that there is no any assistance in this case. So that's why this would be classified as potential energy. So any form of the energy that the object gonna use to move independently, to move by itself, or to deform, or to do any action, to do anything by itself, this type of energy is a potential energy. So we can understand that this potential energy, in other words, the potential energy is the amount of energy that the object uses to move without any assistance. Or simply we can say that an object with potential energy can do something by itself, but an object without any potential energies cannot do anything by itself. It requires assistance if there is no potential. So this is the form, we can understand the potential energy with this form. So how about the potential energy in elasticity? We do have an elastic object. This object would be subjected to some external force. This external force forms like external work over the object, and then the object is going to deform in the elastic way. So in elasticity, the potential energy of an elastic body is measured by its strain energy. And we discussed before the strain energy that we use, the strain energy density function. If you remember, this is W. This is the strain energy per unit volume of the continuum body. So this is strain energy, this is the potential energy that I'm talking about. This potential energy, this strain energy is a stored energy inside the continuum. This what gives the continuum the ability to restore back again within the elastic region. What we understand about elasticity, like if we subject the object into force, and we remove the force, the object gonna restore back again to the original dimension. So how the object can restore back again to the original shape or original dimension, it requires energy to do so. This energy is the strain energy, which is a potential energy. Make sense? So the strain energy is a stored internal energy that the body uses when needed to reform, or in other words, needed to restore back again, or in other words, to be more accurate, or use it to restore back again or restore its original shape and dimensions. Because we said that in elasticity, we do have strains, some of the strains that measure the changes in the dimension and some other measure the changes in the shape. So this is the key idea, that this is the amount of energy that the object uses to restore back again to the original shape or the dimension. It works, as I mentioned, typically like the elastic energy within the spring. So assume that this spring, in this case, we are dealing with this spring like a continuum. This is like elastic continuum body. Make sense? So it's gonna be working, it's going to work the same way. The strain energy is exactly the same as the elastic energy of a spring. To compress a spring, we have to exert some work to do so. This work is energy. Any work, it is energy from physics, right? So looks like you are giving some energy to the spring or to the elastic body. The spring then absorbs this work and stores it internally. So it's gonna become like this work, this energy is gonna become like internal stored energy inside the spring or the elastic body. Then what happens when the spring is released? It uses this stored energy to reset to the undeformed length or shape of the continuum. The stored energy is the strain energy. This stored energy is the strain energy in the typical example of the of elastic springs. So this is the physical meaning of potential energy, and now we have to collect all of these different potential energies, and we said that in elasticity, this potential energy is the strain energy, the total strain energy of the continuum. So since we are talking about the strain energy, let us record the main equations that that used to define the strain energy density function. So here we're going to talk about the strain energy density function, which we used to define it as W, right? If you remember. So the strain energy density function, we said that this W equals 1/2 sigma double dot product of times epsilon, where this is the stress tensor, this is the stress tensor, it is a tensor form, and this is definitely the strain tensor. So this is the strain energy, strain tensor, density function, which is the total strain energy per unit volume. This is per unit volume of the continuum body. So this is this form of the strain energy density function. This is in the vector form. This is in the vector notation, right? If we decided to write this W, but in the index notation, so we're gonna say that W equals 1/2 sigma ij times epsilon ij, right? So this is in the index notation, which is the same function notation. And something that you should understand about this strain energy density function, that it is a scalar quantity. It is not vector, it is not tensor, it is a scalar quantity. So we can, that is fine if we used work with the vector notation, because the dot product of two tensor gives a scalar quantity. Also, this is in the index notation. Also, we knew that from the constitutive equation, that 1/2, we knew that the sigma ij equal the Cij KL, which is the stiffness tensor, times epsilon KL in general, times epsilon ij. We do have another form to this one in case that we are working with isotropic linear elasticity problem. So we do have another form, but let us consider the general form for now. So this definitely is going to give us 1 over 2 times Cij KL epsilon KL times epsilon ij. So this is another form of the an equivalent form of the strain energy density function also in the index notation. The form that I recommend actually to use all the time or to understand the strain energy density with is this general form. It is recommended because all the advanced theories, if we're going to talk about the micromorphic theory or other advanced theories, the strain energy density should be defined in terms of the kinematical variables. But for the linear elasticity, this term, definitely this is going to give us the stress. So that is fine to define the strain energy at the multiplication of 1 over 2 times the stress field times the strain field. But it is recommended in general to represent or to consider the strain energy into this form for the other advanced theories. Anyway, so this is the strain energy density function that we defined. Even we can write this function for the case of linear elasticity, isotropic linear elasticity into this form. Like we gonna have like 1 over 2, we define the sigma as lambda times epsilon kk, or let us use like RR delta ij, which is a dummy index RR, this R, and plus the 2 mu times epsilon ij. This, all of this should be multiplied times epsilon ij. This definitely gonna give us the strain energy density function. For this is for the case of isotropic linear elastic material, linear elastic material. Make sense? So nothing new so far for this strain energy density function. So how about the total strain energy? How about the total strain energy? Remember that this strain energy, it is elastic energy. It is one of the form of the potential energy. It is already potential energy. So this is the total strain energy. How about it? So definitely, as long as this W is the strain energy per unit volume, how about the total strain energy? So definitely, we're gonna give it a symbol as U. So this is the total strain energy. It's gonna be the integration, because this is the per unit volume. So we are going to integrate over the volume of W dV. This integration of V of W, the strain energy density function, over the volume, this is going to give us the total strain energy. So we can simply write this one as 1 over 2 times the integration of V sigma double dot epsilon, if we decided to write this in terms of the vector notation. And remember that this is the total strain energy. Also, it is a scalar quantity because you're already integrating scalar quantity, so it's going to be scalar. That's why we have here the double dot product. Also, if we decided to write this one, so this is in the vector notation. Also, U in the index notation, we can write it into this form as the 1 over 2, the integration of the volume sigma ij epsilon ij dv. This is the strain energy, the total strain energy for elastic bodies. Make sense? But in the index notation, this is in the index notation, but this one in the vector notation. Make sense? So this is for the total strain energy, how we can define it, and nothing new as I mentioned, except that you should understand that the total strain energy, it is a potential energy that is integration of the strain energy density function. So the question is, how about if this is the total strain energy? If this total strain energy is the total potential energy? No, it is not needed. Why? The strain energy is one of the forms of the potential energies, but it is not everything, because we probably do have an object with multiple potentials, like with multiple potential energies. So if we're gonna talk, so when we talk about the total potential energy, it means that we have to sum all the potentials of this object. We have to sum all the potential energies of this object. Like for example, we may have an elastic object that already seated over a table. We put this object at a level from the ground, so it has one potential to move down because of leveling, right? Also it have potential because it would be elastic, so there should be some stored energy as a strain energy embedded inside this object, so it has multiple potential. So when we talk about the total potential energy, it means that we have to sum all the potentials that would be for a specific object. Like you're gonna collect all the potential energies of this object. But in this course in linear elasticity, and this is what conventionally happens for many of the objects, that they do have one form of potential energy, which is just the strain energy. So for now we can deal with this strain energy like it is this total strain energy, like it is the total potential energy. But also there is another thing, like for example, if we do have, let us assume this case. How about if we do have a table, and or forget about the table, assume that we're already hanging a mass M in a cable, and there should be a ground here, right? So, and let us assume that this is our main data. So how about if I decided to cut this cable? What's going to happen to this object is going to move down because of what? Because of its potential. So we're going to say that because of it is already at a level above the datum, so it has potential. So this is one of the form of the potential. But how about if for some reason, while this object is already moving down, we pushed this object. We applied some force onto this object, right? Like we are applied, like this object while it moves down, we just put or hit this object to move down faster. So it will attain a fake potential. It will attain another potential, more potential, but this potential is a fake potential. This is not originally potential. We said that the potential energy is something without any assistance. We give it assistance. This assistance that we give, it is energy, it is work done. It shouldn't be considered like a potential. But at the end, once it hits the ground, it will attain a potential that is faked, right? Yes, because of some external assistance. So this external assistance should be subtracted. But this external assistance, it is in the form of a work done. So we can deal with the work done, and this is this thing that we need in elasticity, because this continuum won't gonna deform unless we subject the continuum into some forces. We have to subject the object to some forces, like the spring. You have to push the spring to give it some energy to be stored, then the spring gonna use this energy to restore back again. Make sense? So this is how it works. It means that anyway, the object should be subjected to some external forces. So this external forces, we can deal with it. We can deal with it like it is a potential, but it is fake potential. Potential that gives assistance to the object. So this type of potential should be negative, should be subtracted, it shouldn't be added. So again, we said that the strain energy, it is one of the form of these potential energies. Any object would have multiple potentials. So to calculate the total potential energy, we have to sum all of these different potentials. Some of these potentials would be external potential. It is not necessary to be internal potential. If it is external that assists the object to move or to deform or to do anything, this assistance or this energy, this external energy, it should be considered as a work done. Or if we decided to deal with it like a potential, we have to consider it as a negative sign. With a negative sign, this negative signs indicate that it is external potential that should be subtracted from the exact stored potential inside the continuum. So that's why here when we're gonna talk about the total potential energy, and this is the new thing here. So we defined here the strain energy. This is one of the potentials. But in addition to the strain energy, there should be another potential due to work done. So this is potential energy due to work done, which we're gonna deal with it like external potential that assists the object. So this type of work of potential energy, which we're gonna give it a symbol as V. So as you can see here, we use even from the physics to give work the symbol W, right? So I'm using here V because if you remember even from the dynamics class, we used to define the potential energy with V. So V here, it is potential energy. We're gonna deal with it like it is potential energy, but since it is external, so we're gonna deal with it to be negative. Why negative? Because it is external of what? What are the things that are as forces, external forces acting over a continuum like this one? We said that from the beginning of this class, like this object, it includes some particles inside the continuum core, right? And these internal particles already subjected to some body forces, F. So this force will result in some movement. It's gonna push this particle to move with a displacement U. So if we multiply the force times the displacement, definitely this is going to give us work, or it's going to give us an external potential, as we're going to deal with it in the minimum potential of the in the total potential energy that we're already discussing here, right? So this is one of the potentials. This is one of the external force, but it is assistive potential that assists the object to do something, right? So this is the body force is a source of a work done or a source of external potential that should be considered when we are calculating or collecting all the potentials of the continuum. But in addition to this body force, there are some other particles that already located over the surface, right? So these are the surface particles. And also we said that these surface particles already subjected to some other forces which are known as the surface traction. So these particles over the surface already subjected to some surface tractions like T vector, right? So this is, all of this should be vectors in this way. Make sense? So definitely the particle that already located over the surface, because of this surface traction, is going to move as well with a displacement U vector in this way. So this T also, it has a work. It is a work done, or it has potential. It is a negative potential. It is a fake potential that should be subtracted. So the total potential in general that would be due to any external force or external potential can be considered as the F vector dot product times U vector. So this is one potential, this is one work done due to the body force, plus there should be another work done, but due to the T vector dot the U vector, which due to the surface tractions. But as you can see, if you remember that this is just one vector acting over just single particle, this U is just a displacement for one single particle. But here, since we are collecting all the potentials, or we are calculating the total potential energy, so we have to do integration over to collect all of these body forces. This is just one force acting over single particle, so we have to integrate to collect over all the particles, or all the body forces, or all the potential due to these body forces over the continuum. So this integration, it should be integration over the volume of the continuum. Why? Because this body force, it is internal force that acting internally inside the continuum, so we have to collect all of them over the volume of the continuum. But how about these surface tractions? These are acting only over the surface. So to collect them, we cannot do integration over the volume, and instead we have to do integration over the boundary of the continuum, or over the surface S of the continuum. So this symbol here, this circle, indicates that we are collecting over the boundary of the continuum. Make sense? So this is going to give us the potential energy due to any external forces. Here we are dealing with these potential energies with these external forces. We are not dealing with it like a work done, but instead we are dealing with it like a potential. So that's why we are incorporating this negative, because this potential, it should be subtracted from the exact or the real potential of the continuum that depend on its stored energy, but this one is external potential. Make sense? So these are the two main sources of potential energies that we're gonna use in the linear elasticity or for elastic bodies, that there is a stored energy, strain energy, plus there is external energy, potential energy comes because of the external force. So if we decided to write here, now we can write the total potential energy. The total potential energy of the continuum. This total potential energy can be written into this form as pi. This is the total potential energy equals U, which is the total strain energy, plus V, which is the external potential energy due to work done. So this is the total potential energy that and how we can define this one. So we can simply write this total potential energy in the vector form. We can write this one into the vector form as 1 over 2 the integration of the volume of sigma, which is the stress tensor, this is in the tensor form, times epsilon dv negative this work done. V, it is already integration of V of the body force vector dot u vector dv negative another surface traction. This is the integration of the over the surface traction dot u vector ds. This should give us the total potential energy, but in the vector notation. This is in the vector notation. Can we write, and remember that again, this is scalar quantity. This is scalar quantity. Again, how we can write this thing, this total potential energy in the index notation is going to be like 1 over 2 the integration of the volume of sigma ij epsilon ij dv negative the integration over the volume of fi ui dv plus negative the integration over the surface of ti ui ds. This is going to give us the total potential energy, but in the index notation. This is in the index notation. Make sense? So this is how we define the total potential energy for the case. This is the total potential energy, which pi, uppercase pi. This is the total potential energy for linear elasticity. Now we're gonna discuss the principle of minimum total potential energy and how we can use this principle to drive the equations of motion, or the essential equation of motion of linear elasticity that we drive it before, but based on this principle. This is what we are going to discuss. Especially we're gonna implement this method for a beam structure, and we're gonna see how effective is this method for solving Euler-Bernoulli beams. Make sense? So as long as we formed the total potential energy, now let us discuss the principle of minimum total potential energy. It is related more to the thermodynamics concept and achieving the equilibrium, that in order to achieve equilibrium of an elastic continuum, we have to achieve the minimization of this potential energy under the static condition. So this, again, that this principle is applied as long as we're already working as elastrostatic equilibrium of the continuum. For the dynamics, the other conventional or the other conjugate principle is the Hamilton's principle, which is already equivalent to this principle of minimum total potential energy, but for the dynamical behavior of elastic continua. But here, since we are working on a static, so we are already discussing the principle of minimum total potential energy. Like we have to do minimization. This delta, this is the variational operator of pi, which is the total potential energy should equal to 0. Something that you should understand about the variational operator, that it is much like the total differential operator d, like you already doing derivative to any function. But the difference between delta and d is that delta operates with respect to the dependent variable u, the displacement, rather than the independent variable x. Like for example, if we're gonna say, assume that you do have like the w, which is the strain energy density function. So if I decided to find the derivative of w with respect to whatever, so you are finding the derivative with respect to x. So this is gonna be the independent variable that we already doing the derivative of this function with respect to it. But the delta of w, you already like you differentiating, but with respect to u, which is the displacement field, rather than the finding the derivative with respect to x, which is the independent coordinate or variable in this case. Make sense? So this is the only difference that, or one of the essential differences between the delta, which is the variational operator, and the d, which is the differential operator. Now what we're gonna do, I'm just gonna show you how we can. So since we are interested in finding the first variation of, this is only the first variation. The second variation is going to be like the delta square of pi it should be bigger than 0. This is the sufficient condition. But anyway, forget about these details. The variational operator of times delta, or the first variation of pi, which is the potential energy, it should equal to 0. So this, it should equal to the first variation of, we already defined pi up there as the summation of U, which is the strain energy, total strain energy, plus the potential energy due to work done. So this is going to be the first variation of U plus V. And then we can distribute even this delta over the two terms. So we're going to have here, it is equivalent to the delta U, or the first variation of the strain energy, plus the first variation of the work done, or the potential due to the work done. So simply to form the first variation of the potential energy, we can find the first variation of the strain energy plus the first variation of V, and this, according to the principle of minimum potential energy, it should be 0. So how about let us here work over forming the first variation of the strain energy. We said that this should be the first variation of the, we define the strain energy at the integration of the W dV, right? And if we decided to do it, this variation can be directly applied to the, it won't gonna affect the integration, because as you can see, the integration, it is over X, or over the volume, and the volume it is dependent on the coordinate, X coordinate, which XYZ coordinates, I mean. So it means that there is no derivative for the volume, because the variation of the volume, it's gonna be 0, right? Because there is no U. This should be doing this delta, it works over U, the displacement field. But this volume is not is not dependent on the displacement field. So that's why its derivative with respect to U, it should be 0, because in V, the volume of the container, is not a function of its displacement, and this makes sense. So giving this or this information, or this fact, then we can carry on, or just move this delta, and it can be applied directly to W. W here in this case, it is dependent on the displacement. The strain energy depends on the generalized displacement of the continuum. So we can write this one as the integration over the volume of delta W, which is the first variation of the strain energy density function dV. So simply to find the first variation of the strain energy, the total strain energy, you have to find the first variation of the strain energy. So now let us work over the first variation of the strain energy here, the delta W. We define delta, and then we define W as the 1 over 2 sigma ij epsilon ij, if we decided to work in terms of the stresses. But actually, I'm not recommending this form. Why? Because if you decided to do the first variation here, it should be done over sigma and epsilon as well. But it would be confusing, but but we can do it anyway. But the key idea that you should understand that there is first variation of the stress, and there is a first variation of the strain as well, because both are dependent on the displacements, right? So if let us write or substitute or write this one in terms of the strain only. So this is going to be the first variation of 1 over 2 Cijkl epsilon KL times epsilon ij. Right, this is just the sigma, just substitute for the sigma using the C, the stiffness matrix, in the general form. Then let us do this delta as like it is derivative over all of these three functions. So you can consider that C, it is a function, also epsilon, it is a function, and this C epsilon is another function. So this like the derivative, finding the derivative of the multiplication of three functions. But remember that this C, it is constant for many of the material, except we said that for function graded material, we may have this C is varying depending on the space, or depending on the position, the coordinate, as a function of X, Y, and Z. But anyway, since this is constant, so we can consider that this 1 over 2 is just constant, so we can move it outside the derivative, and then we can find the first variation of these two variables that already both of them are functions of U. This depends on U, because the epsilon, it is 1 over 2 U I comma j plus uj comma I. So they are already dependent on U. They are functions of the displacement. So they do have first variations. So to find the first variation, this is going to be as 1 over 2 times Ci, or let us just have the 1 over 2. Then we're going to find here the Cij times the first variation of epsilon KL times epsilon ij plus, because this is like you finding derivative of the multiplication of two functions. So you're going to find the first derivative time this time the second function plus the first function time the derivative. So you're going to swap between both of them, right? So this, then we're gonna have here Cijkl, and this we're gonna have here the epsilon KL times the first variation of epsilon ij. So this is gonna be the first variation. So we'll just distribute between the two functions of the two strain tensors here, right? Anyway, so then how about if I, as you can see, this is the first variation, it is epsilon KL, and this is epsilon ij. So try to achieve uniformity in terms of the indices over the first variation of the epsilon. So for example, what I'm gonna do, I'm just gonna change, I need this one as ij, this KL to be ij. So this can be done by having this KL ij. So we're gonna swap the ij with the KL, and definitely this is gonna be KL. So if we did these changes, and that is fine to do these changes, by the way, over this term, we're gonna have this term identical to this one, right? So if we did these changes, we're gonna end up that 1 over 2 times the CKL ij times the epsilon KL, which is this term, and then we're gonna have the delta epsilon ij. Make sense? Plus the Cijkl, the epsilon KL, and this should be delta epsilon ij. So as you can see, the only difference is just the indices of the Cij, KL, and here we do have KLij. But something that you should understand, and this is what we mentioned before about the characteristics of this stiffness matrix or tensor, that these two tensors are the same, they are equal. It means that CKL ij, it should equal to the Cij KL. Why? Because of the symmetry condition or property of this stiffness matrix. So what does it mean? It means that that is fine to consider this one as a common factor. Also we can consider, so, or in other words, as you can see, we have these two terms are two identical terms, so we can combine them and multiply by 2 and times 1 over 2. This is gonna give us just Cijkl epsilon KL, the delta epsilon ij. This is gonna give us the first variation of the strain energy density function in the linear elasticity. So as you can see, this term, which is the Cijkl epsilon KL, this is the stress field, right? This is the stress field times the first variation of the strain field. But remember that this doesn't mean, so if we just combine this one, this definitely is sigma ij, right, times the first variation of epsilon ij. So as you can see that the first variation of the strain energy density function, it is the stress field multiplied by the first variation of epsilon ij, or the strain. If we decided to write the delta W, or looking to the delta W into this form, it would seem that there is no first variation of the stress. There is no first variation of the stress, but in fact there is a first variation of the stress. Why? Because the stress depends on the strain, and the strain itself, it depends on the displacement field. So there should be a first variation of the stress itself. But in this form, it looks like that there is no, or we didn't do variation, but in fact we did, and that's why it is recommended. All the time I recommend to consider the strain energy density function into this form. If we apply the first variation, we're gonna end up with that this epsilon, it has variation, this epsilon has variation, first variation. But since if we simplify the due to the simplification of the expression or the form, we end up that sigma ij delta epsilon ij, but this doesn't indicate that sigma has no first variation for this principle. Make sense? So this is for the first variation. Then we can write accordingly, we can write the first variation of the total potential strain energy. We can write the first variation of the total strain energy into this form at the integration over the volume. And remember that there is no variation of the volume because it is independent of the displacement. This is going to give us the sigma ij, the first variation of epsilon ij dv. Make sense? So this is going to give us the first variation of the strain energy density in terms of the variation of the stress, of the strain, I'm sorry. Make sense? But if we decided to write this one in terms of the variation of U, which is the delta U, which is the variational delta for the displacement. So simply we can substitute for sigma epsilon ij as 1 over 2 ui comma j plus uj comma I, as we agree, right? So plugging this data here, we're gonna end up with this thing like delta U. Here we're gonna form it in terms of the displacement. So this is gonna give us the integration over the volume of sigma ij is gonna be the same, but here we're gonna have the variation of 1 over 2 ui comma j plus uj comma I. Make sense? dv. So how about this first variation? So let us just work here on the side for the delta of 1 over 2 the ui comma j plus the uj comma I. So we can simply have the 1 over 2 as a common factor outside, then we're gonna apply the first variation over these terms. So this is gonna give us the first variation of ui comma j plus the variation of the uj comma I. Something that you should understand about the first variation of the displacement. We are finding for the displacement, but it is not the displacement gradient. Something that you should understand that we can split it. This one, like this term, it can be split into this form. Like we're gonna have here the d by dxj, because this is like the derivative, because this derivative will be carried on, and then we're gonna have the first variation of ui. Remember that the original, this term should be written like delta of the dui by dxj, right? Should be written in this form. So then delta, as you can see, we don't have delta for the derivative. We can split it into delta times d by dxj times multiplied times ui. We can write in this form. If we're already working in the index notation, if we are already working in the vector notation, this delta should be delta nabla, which is the gradient, because this is the gradient operator, times u, which is the vector, the displacement vector, right? This should be the displacement vector. So if you decided to apply the derivative, this is like the derivative of the multiplication of two functions, but in fact this is the first variation of the multiplication of two functions. So this is going to give us the first variation of delta times u vector plus the first variation, the nabla, or the, I'm sorry, this is the delta nabla, which is the first variation of the gradient, times the vector, the displacement vector. Then we're going to have the gradient operator. Then we're going to apply the first variation to the displacement vector itself, like the derivative of the multiplication of two functions. Make sense? This variation is zero. This variation is zero. Why? Because there is no first variation for delta. Delta is dependent on the coordinate system, depends on the x, depends on x, y, and z. But it is not dependent. It is not this delta. This nabla operator, it is not a function of the displacement. So this term will be zero. This is definitely gonna give us delta u, or nabla delta u, which is gonna be the first variation of delta. If we decided to write this one in the index notation, so this is in the vector notation, if we decided to write it in the index notation, will be written into this form. Like this is gonna be the d by dx j times the delta ui, and this is what we're gonna get. So we can say that this definitely, this simply is gonna be like d delta ui by dxj. So you're just gonna carry on the delta over the displacement directly. Then you're gonna have like derivative that it should be multiplied times the other functions. So this what explains that this term we can get it directly as the d by dxj times the delta ui. this term is going to be the same. This is going to be the d by dxi, because the derivative with respect to I, the delta uj. This is going to give us the first variation of these two terms. Make sense? So if we did so, this derivative, and we plug these things here, this derivative will be applied to the sigma. This derivative will be applied to the sigma, and and this delta u or delta j will be we're just gonna consider them, right? So doing so, we're gonna end up with this first variation of the u. This is gonna give us the first variation of the strain, the total strain energy, into this form at the integration of over the volume of sigma ij. Then we are going to add here the first variation, this term, we're going to have here 1 over 2. So this is going to give us like delta 1 over 2. This term will be plugged here. I mean, like we can simply even distribute the sigma over these deltas. So we can, and we can have the 1 over 2 just as a common factor outside here. So we're going to have here, just let me have the 1 over 2, the integration over the volume. This is going to give us the sigma ij times the delta ui comma j, one term, plus there is another term, sigma ij, the delta uj comma I, and all of this should be dv, right? I just distributed the sigma over this term. Now we're going to do this derivative, right? We're gonna apply this derivative, but remember that this derivative is already applied over integral here, over integration. So we have to consider the integration of the integration by parts to perform the integration over these two multiplied functions. And according to the fundamental lemma of variational calculus, we can write this term here. I'm just gonna show it for. I'm gonna show you this term, just this one single term, the integration over the volume of sigma ij times the delta ui comma j dv. So this term, it can be expanded because we have to isolate this delta ui. We need to get rid of this derivative, right? But we can do it as we did it here, right? We can write this one into this form. And then we're going to apply this derivative over the sigma ij. But this will result in some surface tractions as well, as I'm going to show you according to the lemma, the fundamental of lemma of variational calculus, or the variational calculus in general. So this is going to give us equals, this term will be the integration over the volume of sigma ij. We said that we can isolate the derivative, we can get rid of the derivative, and we have the delta u. So this derivative will be applied directly to the sigma. Make sense? Then we're going to have the first variation of ui. This is going to give us the integration over the volume plus, I'm sorry, and there should be here something that you should understand. According to the variational calculus, like if we applied one first derivative over any variable, that this derivative we obtain this one because of the first variation, this is gonna give us negative sign. There should be negative sign here, right? But if we do have like second derivative, like assume that we do have here like jj, so there should be another j, so there should be like two negatives. So this is gonna give us negative times negative, this would be positive. Because how did we know these things? Because if you're gonna obtain the same thing if you did the integration by parts twice. If we did it twice, this sign will be positive. If we did it once, we're gonna end up with a negative sign here. So generally, if you're already doing, just to make it simple and don't spend time doing the integration by parts, if you are doing first derivative to this variable, whatever this variable is, it would be displacement, it would be strain, it would be stress. Since you are already applying one first derivative on every single derivative, it's gonna take a negative sign. Make sense? Plus, there should be another integration, but over the boundary. That this phase variation, it won't gonna affect only the bulk, it will also affect the boundary as well. So there should be here something because of this phase variation over the boundary, over the surface of the continuum. This is, as we mentioned, this is integration over the surface of the same sigma ij, but over the surface whose normal is going to be nj. Why nj, not nk or I or whatever? Because we already doing the derivative with respect to j. So this is as long as there is derivative with respect to xj, so you have to apply here the nj. If it is I, so it's going to be ni, k, and so on, of the same variable, of the same stress, strain, or displacement. Then you're going to have the delta ui. All of this integration should be done over the surface. So this is the original form. As you can see here, we are applying the first variation to the gradient of the displacement. But in fact, according to the minimum of potential energy principle that we are going to apply, we need to have the first variation of the displacement only, not of the gradient of the displacement. Make sense? So to do so, we had to get rid of this derivative. So this derivative will be moved to affect directly on the stress. So it will be acting over the stress, as is already given here, but in addition, it will also result in some boundary condition. So this is the key idea. This is the importance of the variational method. It gives us an idea about the boundary condition, and the boundary condition is it will be automatically formed, as already given here, because of applying this is according to the variational calculus principle, that we're gonna end up with this boundary condition will be automatically formed. If we did the same to the other term, to the second term here, we're gonna have the integration, because we can distribute the integration over these two terms, sigma ij, the delta uj comma I. Now the derivative with respect to xi, dv. This term can be split into two terms to isolate the first variation. Instead of having it over the gradient of the displacement, to have it over just the displacement. This is going to give us negative, because we do have only one single derivative of the integration over the volume of sigma ij, but comma I, because we're going to do the derivative with respect to I, times the first variation of the displacement dv, plus there is another variation but over the volume, over the surface, I'm sorry, which is going to give us the sigma ij ni delta uj. Remember that this should be uj because it is uj already, ds. Make sense? So this is simply how we can apply this variational calculus things to these two terms. So if we did so, we're gonna end up with the first variation. We're gonna end up with the first variation of the strain energy into this form will be 1 over 2, which this 1 over 2, the integration will be distributed. If we did the integration over this one, it had been split into two terms. So we're going to have here times the negative of the integration over the volume of the first term, which is the sigma ij, comma j, the delta ui, and also there is another term here. This is the first variation of the second term, which is going to be the plus, because we're already considering the negative outside here. This negative sigma ij, comma I, delta uj, dv, plus, so this is the first, this is the volume integral. Then we do have here integrations over the surface. So we're going to have the integration over the surface. We do have two terms. The first term, which is the sigma ij nj delta ui, plus the second term, which is the sigma ij ni, the delta uj ds. So this is going to give us the expanded form of the first variation of the strain, and this is what we're going to do all the time for using this variational method, that the key idea that we should have the first variation of the displacement only. If we do have the first variation of the gradient of the displacement, we have to get rid of it based on the concept of the variational calculus and the integration by parts. So we're going to end up with these expressions. Make sense? So this is for the first variation of the strain energy. So going back here to the first variation of the total potential energy, we said that it should be the first variation of the strain plus the first variation of the potential due to work done. We already worked over this one, and we drive it the first variation of the strain as we did here. Now let us form the potential, the first variation of the potential due to work done. So this is gonna give us this thing. So here we're gonna work over the first variation of the potential due to work done, which should be the first variation of the integration over the volume of the body force ui dv, right? Plus, and it should be negative, by the way, right? So there should be negative and negative here, the integration over the surface of the Ti Ui ds. This is just the expression of the potential energy due to work done, right? Because of these body forces and self-instructions. Make sense? So now we're gonna distribute this delta and we're gonna apply the delta over these things. But we have three things for each term. We have the integration, and we said that there is no first variation for the integral because there is integration over the volume or even integration over the surface, and these surfaces and volumes, they are not functions of the displacement of the continuum, right? So it means that there is no first variation of the integral itself, but we probably may have a first variation of the body force or the displacement itself, but even the first variation of the body force, it should be zero. There is no variation for the body force with respect to the displacement. Why? Because the body forces or even the surface tractions, these are external fields, and in many cases they are not dependent on the displacement of the continuum. They are constant unless we have some special types of elastic continua that they probably do have the body forces depends on the displacements. So in this case, there should be a first variation for this body force or even the surface traction. But in the conventional use of the linear elasticity, these body forces and surface traction, they are independent of the displacement fields. So that's why they don't have first variations. So if we decided to do, so this indicates that the integral and the body force and the surface traction and the surface, all of these four quantities, they are independent of the displacement and they don't have phase variations, so that we can deal with them like constants. So the only thing that it will be subject to the phase variation is only the displacement field ui. So we can write this thing as the negative of the integration over the volume of fi is just constants. The first variation of ui directly, the first variation will be applied to the ui dv, negative the integration over the surface ti, this constant, the first variation of ui ds. This is gonna give us simply the first variation of the work done. So in general, we can write then, generally, once we end up with this thing, we can write the minimum of potential energy principle into this form. That is said that the first variation of the total potential energy should be zero, which we already drive it this term into this form. So this is going to give us 1 over 2 the integration. We can even have this negative outside here, anyway, because there should be another square bracket here closing because all of these terms will be multiplied times half. So this is going to give us 1 over 2 times the negative of the integration over the volume of the sigma ij comma j delta ui plus the sigma ij comma I delta uj. Even we can combine this volume term because we do have here integration over the volume one term, two terms here, then we can add these two terms as well to them. So this term, this term here. So this is going to give us also plus the fi delta ui. All of this term will be integrated over the volume. Make sense? And there should be a negative here, which is this negative and this negative. But how about the other term? The other term here, this should be, I'm sorry, we should have the 1 over 2, it should be inside the square bracket. So this is going to give us definitely negative, or we can remove this just to write the 1 over 2. So it should be written like 1 over 2, right, times these two terms. Then we're going to have here a square bracket in this way. And we're going to have here the integration over the volume, and there should be negative outside. Make sense? To be more accurate. Then we're going to have here the plus of, this should be plus the integration over the surface of what? We do have here the sigma ij nj delta ui plus the sigma ij in I delta uj, and we do have also the negative of ti delta ui. So this is going to give us the sigma ij nj delta ui plus the sigma ij ni, the delta uj plus, or it should be negative, the ti, the first variation of ui. All of this should be integrated over the surface. So this is going to give us all of these terms should be zero. So you could say that this equation of the first variation of the total potential energy sum to zero, this is going to give us, we can split it into body equilibrium equilibrium over the continuum, which gives us the equilibrium equations, and these are the boundary conditions. As you can see in the first variation, we can form the boundary conditions in terms of the stresses, in terms of with anything in relation to the surface tractions. So this is the good thing of this variational method of the principle of total potential energy. Make sense? So what I've did here, what I've done here, I just discussed this principle, and we knew how we can drive these equations, and we can form the first variation of the total potential energy in terms of the displacements and the stress fields. Even we can remove, we can substitute, we can plug the substitute for linear elastic isotropic material. We can substitute with the sigma as lambda times epsilon r delta ij plus 2 mu epsilon ij. We can plug it here, so we're gonna end up with the field equation, which is known as Euler equation. Okay, we can do so, but what I'm gonna do next, I'm just gonna give you an example on using this variational method for the beam structures, and we're gonna solve. I'm just gonna show you how we can form the total potential energy and the first variation of the total potential energy for a beam, an Euler-Bernoulli beam, and then I'm going to show you how we can solve this beam structure analytically. Make sense? So this is for this principle, and in the next video I'm going to show you how we can do apply this method to beam structures. Thank you, and see you in the next video.